Hello, everybody. So now we are moving on to the next topic under solution thermodynamics, and this is on the ideal solution model. But just to recap, before what we dealt with was on ideal gas mixture. So I'm browsing uh, to the initial slide. So here last time we have dealt with the ideal gas state mixture model, and we said that there are simplifying assumptions to make the calculations easier, and it's the same way for the ideal solution model. So there are also the same simplifying assumptions or similar simplifying assumptions. So let me jump back to the ideal solution model slide. Okay, so um, again, the reason why the ideal solution model is important is because although it's an idealized model and it has simplifying assumptions to make calculations easier, we can use it to serve as a reference or starting point to understand the more complex real solution behaviors. So it provides like a useful approximation and the foundation for more advanced models and calculations. That's why we are studying the ideal solution model. And just recall from the ideal gas state mixture model. So before that, let me just run through the simplifying assumptions of an ideal solution model. So like in the ideal gas mixture model, it's assumed that the molecules are more or less similar in size and shape, and that the intermolecular forces of attraction between um, like and unlike molecules are more or less equal. Uh, so so these are similar to the assumptions under the ideal gas model. All right. So remember, we have this equation from the ideal gas model for the chemical potential. We can extend this equation for the ideal solution. So extending the equation, as you can see, uh, we replace the partial molar Gibbs free energy um, for the ideal gas. We represent it now with a superscript ID, right, to represent the ideal solution. So this is now the partial molar Gibbs free energy for the ideal solution. Okay. Next, instead of using y sub I to represent the components of the substances in the mixture, we represent it by convention with x sub I. So x sub I is the mole fraction in the ideal solution. So all the other thermodynamic properties for an ideal solution follow from equation 1. Okay? And these are the equations that I'm referring to. So what do you notice? They look similar. Right? They look similar with the equations to ideal gas mixture. Um, However, take note that the temperature and pressure dependence are not those of the ideal gases but are given by the pure species property. Okay, so let me jump back to that slide on the ideal gas equation so that you will remember. All right, this one. Uh, these are the equations for the partial molar properties of the ideal gas and the total property of the ideal gas mixture. as you can see, uh, the expressions are analogous for ideal solution. We just simply replace the IG here to ID to represent ideal solutions, and using XI instead of YI for the composition. Right. Let me go back to the ideal solution equation. So we can use these equations to solve for the properties. Uh, Volume, enthalpy, internal energy, entropy, and Gibbs free energy, partial molar properties, and the total properties in an ideal solution. Next, let me introduce the Lewis-Randall rule. Okay, so for the Lewis-Randall rule, uh, this is the equation, which is the fugacity of the species in the ideal solution, and that is represented by Fi hat, if you will remember. So in the previous lectures, um, we said that the fugacity of the components in an ideal solution is represented by the hat symbol right there, and it's equal to the mole fraction multiplied by the fugacity of the species. And applies to each species in an ideal solution at all temperature, pressure, and composition. So as I mentioned, it shows that the fugacity of each species in an ideal solution is proportional to its mole fraction. And the proportionality constant is the fugacity of the pure species I in the same physical state at the same temperature and pressure. Okay, so Fi is the pure species fugacity. So if we have that and we know the mole fraction, we can calculate the Fi hat, or the fugacity in an ideal solution, fugacity of the species when it's in the ideal solution. Now, if we divide both sides by Pxi, or the pressure times the mole fraction, we get an expression for the um. So if you will remember, this so xi will cancel out from the numerator and denominator, and if you will remember, the fugacity divided by the pressure gives us the fugacity coefficient. Therefore, the fugacity coefficient in an ideal solution, or phi hat, okay, is just equal to its fugacity coefficient as a pure species I in the same physical state at as the solution at the same temperature and pressure. Okay, so by derivation we have shown that these two quantities are just equal. Okay, let's move on to the next topic, which is on excess properties. So, just like in gases, we have residual properties, which is equal to the actual property minus the property of an ideal gas. In solutions, we have a analogous relationship between the actual property and the property of an ideal solution. And that is what we call the excess property. So formally, it's defined as the difference between the actual property and the the value it would have as an ideal solution at the same temperature, pressure, and composition. So by definition, we assign excess property, and just take note that the M here is a molar or unit mass value of any thermodynamic property: volume, internal energy, enthalpy, entropy, or Gibbs free energy. Okay? So we have this definition, and we have the definition of the residual property for ideal gases. Um, if we subtract the two equations, okay, so it would give us this difference, all right? And then remember that we can use the summability equation, okay? The summability equation, and that would give us the summation of the mole fraction times the residual property, okay? Therefore, um, the excess property is just equal to the residual property minus the summation of the mole fraction multiplied the residual property of each species I. Okay? So it's important to note that for solutions, um, excess properties for pure species have no meaning. But for gases, residual properties exist both for pure species and for mixtures. Okay, therefore, we can write the partial excess property as in this equation. Okay, so right now it's the partial excess property, and what's the point of calculating the excess property? So again, this is important to us because excess properties refer to the deviation of a real solution from an ideal solution, and therefore uh, we can use it to um, measure real solution properties. Okay, so that's why it's important to us. And remember, we have this generating function. I still hope that you recall this generating function from the previous lectures. So from here, uh, we express the generating function of the Gibbs free energy in terms of excess property. So it's now G superscript E, and all of the properties are excess properties. We can use this generating function to derive expressions. We can use the generating function to derive expressions for the other properties, um, like for volume, entropy, enthalpy, and also for the specific heat. So what do you notice? We have expressions for volume. So how did we come up with this uh, equation for volume? If in the generating function, if we set the temperature and composition as constant, then we are left with the left side of the equation and the first term. So with that, we're able to derive this first equation and just do the same for the rest of the equation. For enthalpy, we can use the um, this relationship, H equal to G plus temperature times entropy. And we can express all of these properties in terms of residual for ideal gases and in terms of excess property for ideal solutions. So just we use the different superscript for residual and for excess properties, but still using the same generating function. So what is the importance of doing this? We can see it later in the example, which we will do next. I will just pause for a while to get my writing pen. Okay, let's answer this problem. I'm now showing the whiteboard with a problem. So this example would demonstrate how to calculate the excess properties using the generated equations uh, in the table that I have shown earlier. So again, the relevance of that excess properties. If we compute the excess properties, then more or less we have a value of the deviation from the ideal behavior. Okay? And if we know the ideal behavior, then and we know the deviation, then we can get the property of the real behavior. So let's read the problem. If the excess specific heat is a constant independent of temperature, find expression for the excess properties of G, S, and H as a function of T. Okay, that's for letter A. For letter B, from the equations developed in part A, find the values for G, S, and H excess properties of G, S, and H for an equimolar solution of benzene and N-hexane at 323.15 Kelvin. Given the following excess property values for an excess equimolar solution at 298.15 Kelvin. All right. So the first step is to derive expressions for these properties and then use those expressions to solve for the actual values. And we're given um, the the excess property of the same solution, meaning it's also equimolar, but at a different temperature. So the one at 298.15, they are given, but um, what is being asked from us is to find the values at a different temperature at 320.15. So first, let's write the given. Okay, hold on. Given, oops, given the specific excess specific heat is a constant. So let's assign for convenience it's letter A. So A is a constant, where A is a constant. And then it's temperature independent. Uh, it's T independent. Okay. What else is given? Values for uh, G, S, and H. I mean, CP, H, and G. Okay, so given the values, so oops, equimolar benzene, so this is species 1, and N-hexane, species 2, at 298, so this is given Kelvin. So for equimolar uh, solution, the CPE is negative 2.86 joules per mole Kelvin. The HE is 897.9 joules per mole. And the GE is 384.5 joules per mole. What is being required from us is letter A expressions for GESHE expressions as a function of T, as a function of temperature. And then letter B, they're being asked for the actual values G S SHE values at T equal to 323.15 Kelvin. Okay. So what's the first thing to do here? Solution. Again, we have let CPE equal to A, where A is a constant. Let's go back to the table to get an expression for CP. Okay, let me go back to the slides here. All right, so can you see it at the bottom of the last column? We have an expression for CP in terms of Gibbs free energy, okay, at constant pressure and composition. Okay, so we use this, we copy this one to our solution. Okay, we go back to the whiteboard. So I'm showing the whiteboard now. We write CPE, okay, from the table. So uh so that's negative temperature, second order partial derivative of GE with respect to T, okay, at constant P and composition. All right. So in terms of if we replace CPE with A, then this one becomes uh, A, or rather, let me write it this way. Second order GE over, with respect to T is equal to negative A over T. So just replacing CP with A and moving negative T to the left-hand side of the equation. So our equation is transformed to this one. So we want to derive this equation, and what we get is um, the first derivative would give us this expression, okay? Negative A ln t, right? Plus an integration constant. Okay, so B is an integration constant. So this came up when we derive uh this equation. I mean, not derive. What I mean is integrate. Okay, we integrate this once. Okay, we integrate the equation once, and this is the integration constant. Okay. Next, we integrate it once again. Let's integrate that once again. Okay, we integrate that once again, and what we will get is, so I'll skip the details on the integration. Please just review your integration lessons. So that's T ln T minus T plus our integration constant multiplied by T plus C, which is another integration constant. And this is actually one of our answers for letter A. Okay, for letter A, which is an expression of excess property G in terms of temperature. Okay, so let's name this as equation A. So now we have an expression for the excess G. How about for the excess S and excess H? Okay. For the excess S, let me go back to the table again. Okay, so let's as you can see for the excess S, this is the equation. We copy this is the second row, last column. We copy it to our solution. Okay. So from the table, SE is negative partial of G with respect to T at constant pressure and composition, right? And then next, uh, so what do you notice? By the way, what do you notice? Our first integration, okay, our first integration here, okay, is actually equal to S, excess S, or the excess entropy. So we can write it as, um, so we write this one, negative A, L, N, hold on, negative A, ln T plus B. And that is actually our answer, okay, for the expression for entropy. Let's name it as, oops, letter B, equation B. So now we have expressions for Gibbs free energy excess and entropy excess in terms of temperature. The last property that we need to derive is H. So we start by using this definition of H plus TSE. Okay. So what do we need? We actually just need to combine equations A and B right there to get HE. So we do that. We do that. Uh, we write G by negative A T ln T minus T plus BT plus C plus the temperature right here multiplied SE negative A ln T minus B. Okay? And then we simplify the equation, that is going to be negative AT ln T plus AT plus BT plus C. So just copy that. Oops. Okay. I have a mistake right here. Alright. So the negative sign cancel out the negative sign of A L and T, and this one should be negative. Okay, so please correct your notes. Okay, so this is the final equation. So because of the negative sign here, this cancels out the negative here and negates the constant B. So what happens here is that this one is, oops, this should be positive. Right. So with that, this is A T ln T minus BT. And then this one cancels out this and BT cancels out this. So HE is AT plus C. And this is the expression for HE. So now we're done with letter A. We have the expressions as a function of T. We move to letter B. Okay, so we solve letter B. which is to get the actual values, but we have a problem. We have integration constants. Supposedly we're going to use these equations, but the problem is that we have integration constants B and C. With regards to A, this is just CPE, which we let A be equal to that earlier. Uh, so what we would do right now, okay, so by the way, since it's given in the problem that CP is in the temperature independent, therefore, if CP is in temperature independent, then um, remember we have values, okay, we have given values for CP, HE, and GXS at a different temperature. So let's name this as the temperatures. The temperature 298.15 is our reference temperature T naught. So all of these values at the temperature would be our reference values, and let's name them as properties with naught. Okay. So at T naught equal to 298.15 Kelvin. Okay. Then our CP is CP naught E. Our HE is also HE naught. And our ChE is ChE naught. Okay. Going back to CP, since CP is temperature, since CPE is T independent, then CP is just equal to CPE naught, and it's equal to the given 2.86 joule per mole Kelvin. So this is given right here. Okay, so this is CP equal to CPE naught because it's temperature independent. So regardless whether it's a 298 or a 300, what's the 323.15, CP is equal to this value. Next, our next goal is to solve for the integration constants before we are able to use the equations to solve for the actual values. All right. Let's look at equation C. Equation C. Equation C. Um, in if we express this in terms of HE naught, okay, then from equation C, HE naught is AT naught plus C. Do we have A? Yes. Our A is just CPE. We let that earlier, right? So this is CPE. We have T naught. We have H naught that is given. So therefore, we can solve for C. So, and that is HE naught minus AT naught. And substitute HE naught. So that is given right here. Because we let all of these properties at 298.15 be their reference state. So HE naught is 897.9. 9 joules per mole minus not A naught. So that's negative 2.86 joule per mole Kelvin. Okay. Times T naught, which is 298.15 Kelvin. Okay, so our units are agree for the first and second term. C is equal to 1750, 1750.6 joules per mole. So that is letter C. The only thing remaining is letter B. So using equation A, okay, let's go back to equation A. Equation A, this one. We have A, we have B, uh, we don't have C. So we express equation A in terms of the reference state. Doing that and solving for B would give us this expression. So this is now in terms of uh, the reference state. And I already isolated letter B on one side of the equation. So just please do the intermediate steps on your own. Okay, so this is equation A, isolated letter B on one side, and expressed everything in terms of the reference temperature and gives free energy. We have values for G. It's given right here. And we have, we know A, it's equal to CP. T naught is 298. C, we have solved it earlier. Just substitute everything. So after substitution, okay, you will get letter B equal to 18.0171 joules. And you should know the units, joules per mole Kelvin. Okay, so please do the intermediate steps on your own. So now that we have expressions for A, B, and C, let me write them. Let me summarize our constants. Letter A is just equal to CPE, negative 2.86 joules per mole Kelvin. Letter B is negative 18.0171 joules per mole Kelvin. And letter C is 1750.6 joules per mole. Okay? Now we can substitute back into the equations ABC. And doing that, let me demonstrate one property. So for letter B, we're being asked for the actual values of the excess properties G, S, and H. Let me demonstrate for G sub E. Okay? Um, so for G sub E, equation A, okay, equation A, so let using equation A, okay, GE, and now I'll directly substitute 2.86 joule per mole Kelvin, okay, multiplied by, okay, so for the temperature, use the required temperature, 323.15 Kelvin. Okay, 323.15 Kelvin, Ln 323.15 Kelvin, minus, so this is, okay, plus, so let negative 18.0171 joule per mole Kelvin, multiplied by 323.15 Kelvin plus 170 joule per mole. Okay, so far, our units are consistent, joule per mole. So what we will get here is 344.4 joules per mole. So this is G, excess G. Now for the rest of the property, just do the same. Do the same for SE and HE using equations B and C. So after substituting the values, what you will get are SE, that doesn't look like an E. SE equal to 1.4 92 joules per mole Kelvin. Okay, so and also for HE, what you will get is 826.4 joules per mole. Okay. All right. So this actually ends the example 7. All right. All right. So now we move back to the lecture slides. Um, we're still in the ideal solution. Just forgot to tell you that, hey, in this equation, the first term is temperature and pressure dependent. So the Gibbs free energy of species I, that would be temperature and pressure dependent. And the second term is actually, or that this term actually shows the composition dependence due to the entropy. Okay. So entropy because or entropy increase due to the random intermixing of the molecules of different species. Okay, so I forgot to tell you that in the introduction of today's lecture. So we that is reflected in ideal gases, and because it can also be that behavior is also reflected in ideal solutions. So that's why we can uh, use this analogous equation for both gases and solutions or gases and liquids. Okay, so now that we're done with uh, example 7, we move to the next slide, which is the nature of excess properties. There are peculiar behavior of liquid mixture that are revealed in excess properties. Particularly, we want to focus on Gibbs free energy, enthalpy, and entropy, which we can observe using experiments. So, for example, HE or enthalpy excess is determined by mixing experiments, and we can derive entropy based on the definition of G. So, actually, excess properties are not strong functions of temperature. Um, I'm sorry, I meant excess properties are often strong functions of temperature, but at normal temperature, they are not strongly influenced by pressure. Okay, let us look at so that is for temperature and pressure. So again, excess properties are strong functions of temperature. That's why in our example, right, we derive expressions for G, S, and H excess in terms of P. Okay. And then at normal temperatures, okay, they are not strongly influenced by pressure. So they are a weak function of pressure at normal temperature. So what we usually use normal temperature is 20 degrees Celsius, but uh, please check uh, the definition of the normal temperature. How about the composition dependence? So we describe the temperature and pressure dependence of excess properties. How about composition? So this is shown in the next slide. What do we observe? Okay, so these are graphs of excess properties of 6 binary liquid systems listed below in the description of the figures. We have chloroform and heptane, etc. Okay. The reason why they presented different binary systems is to make some generalizations. For example, so we can so here we have the enthalpy, entropy, and Gibbs free energy excess graphs versus the composition X. Okay, what can we generalize or what can we observe? All the excess properties G, S, and H become zero as either species approach purity. So if it's a binary system, so once if x equal to 0, that means uh, x1 is 0, then that means x2 is 1 or species 2 is pure. It becomes purely species 2, right? And at either pure substance or species, the excess property becomes 0. And that is expected because um, of what we derived earlier. Okay. We said earlier that excess properties have no meaning for pure species because, as shown in the figure, for pure species, excess properties just becomes 0. Okay. Next is uh, uh, G, I mean the shapes. For Gibbs free energy, more or less it's parabolic in all of the systems. But for enthalpy and entropy, they have a character or individualistic behaviors or composition dependency. Like, for example, this one, it's not a parabola. Okay? And also for entropy. But for G, it's more or less parabolic. And if the property has a single sign, so what does that mean? If a property just lies on either on the positive y or the negative y region or above the x-axis or below the x-axis, which is true for G. Okay, as you can see, G is just either above or either below, but not but unlike H, like here, as you can see, it's above and below the x-axis. Then, like G, the extreme values of the property often occurs near the equimolar composition. So equimolar meaning x1 is 0.5, x2 is 0.5. So it means the deviation from the ideal solution occurs often near the equimolar composition where x1, x2 is 0.5. So those are just generalization or generalized behaviors observed using the excess property graphs for H, S, and G. Alright, so this ends the lecture on solution thermodynamics. Our next uh, topic would be mixing properties. Okay, so I will end the video.